I'm really proud to be here for Recon. I'm extremely scared because it's Friday the 13th, and I'm presenting at 10:30. Remove the zeros, that's another 13. That's crazy. So it's an honor to be at Recon. As you see, the title of my presentation is How I Learned Reverse Engineering with Storm. So this is an honest fact. I've been following the Stormworm for the last year and a half and really learning from it, because every time a new sample would come out, I'd open it inside a debugger or inside IDA and have a look and see how it was working. So the real objective of my presentation is not to show you how good and clever I am, because I know lots of people in this room are much better than I am. But I really want to share some reverse engineering experience. And by the way, I also want to break some of the myths about the Stormworm, because it's not the thing that's going to kill everyone, of course. And hopefully I will also be able to learn from your comments and recommendations that you can send me afterward by email or right after this presentation. Here's a quick outline of my presentation. I want to start with the general overview of Storm. So this is not a technical overview, it's really a brief history. And then I will go into the technical details and their evolution, including the packer that has been used, some rootkit and system drivers, browser exploits, etc., etc. So there has been various names applied to the Stormworm. The most commonly used one is newr, which has been given by Microsoft, Trend, McAfee, and ESET. By the way, ESET is my employer, so you see the nice logo on the right. Symantec calls it PCOM, and Kaspersky calls it Zlatin. We've sometimes seen samples being called by other names, but they are just confusing. They're not the good names. For example, PID, TIBS, and XPack are the name of the packer that is used to wrap around the executable, so it's not really the name of the thread. And same thing for fooclip. Fooclip is really the rootkit component of this thread, and it should not be used to describe the complete executables of the Stormworm. Now with a brief history. The first files we've seen from Storm appeared in the fall 2006. They were distributed as attachments to emails, and the titles of the email were something like Nuclear War Against Iran. So this is where newr comes from. And we've also seen emails with full clip of Saddam Hussein execution, so this is where the name fullclip comes from. But the name Storm really comes from the Storm Kirill. Have you guys heard of the Storm Kirill? Any people from Europe here? No one. Come on, there has to be at least someone. Well, Storm Kirill hit Europe on January 17th of 2007. And I know that our company got really hit badly because we lost power for a couple of hours, and there has been lots of damages. I think 2 or 3 people died in Europe because of this storm. But the name comes from, the Stormworm has been called like this because as soon as this storm hit, they started sending spam saying, oh, look at the video from Storm, and then you could double click on the executable and have lots of fun with an infected PC. So after that, we are seeing new propagation waves of the Stormworm with almost every special date on the calendar. For example, Valentine's Day, Easter, everything else. So can you guys in the back still hear me? Is everything all right? Yeah, falling asleep? Not yet? In terms of infection vector, Storm usually propagates through email. So this is not really interesting technically, but it seems to be the more effective infection vectors because everybody reads their email and everybody likes to click on everything they see. So inside the email, you would get just a quick sentence and saying, oh, go click on this link. So the social engineering scheme is relatively successful. But we've also seen other infection vectors, such as browser exploits. The file would copy itself to removable drives as install.exe. So if you remove the drive, stick it in another computer, then you have chances of affecting this new computer. But also affiliate programs. This is a new trend in malwares where you will have one gang that's going to pay the gang next door for them to install your malware. For example, if you have 2 botnets, the guy behind this botnet is going to pay this one to install their malware on this one as well. So you just doubled the size of your botnet. And it works. I mean, people are paying for that. There are a couple of examples of social engineering because Storm is not only evolving on the technical level. The guys behind it are also investing time into making nice and credible social engineering campaigns. For examples, we had the laughing psycho kitty cat. That was in Flash, and extremely annoying to me because it has sounds and moves, and it's really, really awful. We also had the arcade game world, where people would be redirected to a web page, and everywhere you click on this page, you get an executable that is, of course, a new variant of Storm. Then around Christmas, we had some spicy screensavers. And if you can't read there, it says, "Find out what is keeping Santa so jolly." Thought it was interesting. The most successful in social engineering campaign from Storm has always been postcards, either electronic cards, electronic postcards, and they are coming back to this theme again and again and again. So this is a good way to see that they are monitoring the success rate of their campaign, and whenever a good theme is found, they will come back to it and use it again and again. And on April's Fool, we also had some cool images. In terms of number of infected hosts, Storm is using a decentralized network. I'm going to give a lot more detail on that later, but it means that all the infected hosts are not going to enter into communication with a specific central command and control server. So it's very hard to have a good estimate on the number of infected hosts. So Microsoft in September released an update for their malicious software removal tool that would help remove Storm from any PC that has accepted to run this tool. And they claim that they disinfected 275,000 machines. There is a slight nuance here that has to be introduced, is that these machines might have been infected, but they didn't necessarily communicate with the rest of the botnet because they might have been sitting behind firewalls and things like that. So this is really the higher bound that I could find for the number of infected hosts. On the other hand, Thorsten Holz's team did some very good research where they would crawl the peer-to-peer network and try to find all the infected hosts. And their estimate is that at the lower bound, they found 6,000 machines participating into the botnet and 80,000 as the higher bound. And my company has a central reporting system where we receive reports of any infection that occurs, and we receive about 10,000 detections per month. But this is not really a number of infected hosts because we've detected the thing, and well, it's just an executable that was thrown at a computer. Now, the purpose of this whole operation is to create a botnet. And the botnet has been used for various purposes. The first one and main one is spam. They're always sending spam with the botnet. They've also used it for denial of service and distributed denial of service against other gangs. I thought it was interesting because they're really acting like gangsters. If they see that another gang is stealing some of their business, then they're going to attack it. And also they had automatic denial of service against researchers. If you spend a bit too much time poking around at an infected computer, you might attract their attention and receive a huge denial of service. The rumor has it that Diego went out of internet for like 15 minutes because somebody has been paying a bit too much attention to Storm. We have propagation. Of course, the botnet is used to send more emails. And finally, pump and dump. So who is familiar with this term? That's 1, 2, 3. Oh, come on. So pump and dump scams are where some malicious actor will buy stock from the stock market and then start advertising it and hope that the price is going to raise. So if you buy lots of stock that is worth 1 cent, you wait for it to get to 10 cents and then you sell the whole bunch of them. So that means that within a couple of hours you can have 10 times more money than you had before. After that, the botnet has also been used to harvest email addresses. So if you get infected by Storm, the malware will parse your hard drive and try to find any email address that it can find, and then you will receive lots of spam. They also participate in affiliation programs where they will install other malwares on your computer. For example, Bankers, which is kind of malware that will steal your bank information. My last bullet is who knows, because the operations of Storm are really well planned out. And they will never use the whole botnet for an operation. They will only select a subset of the infected computers to, for example, perform a spam run. So I thought it's very interesting because it's going to be very hard to find out exactly what the botnet is doing at every time, because the infected hosts are not all doing the same thing. If you want to follow the rest of this presentation or take it offline and have a look, and then you will need some binaries, because the rest of the presentation is about the technical details. The easiest way is probably to check your spam folder, because Storm has been sending out samples for the last year and a half. But also, if you find an infected host on your network, just make a request on the HTTP port, and you will be redirected to a page serving malicious files. There's also Google. Just search for some of the strings that you see in there. And offensive computing. If you guys don't know about it, it's offensivecomputing.net. It's a very good project where you can find more analysis on Storm, but also thousands of binaries. Now, let's start with some technical details on the Packer. Okay, so this is Recon. How many people here know what a Packer is? Excellent. So I don't have to explain what it is. For those who don't know, you can see it as a wrapper around the executable that will help protect it, right? The Packers with Storm are very interesting because they will develop a completely new one every time they want to do a propagation wave. So this is clearly to evade antivirus detection and make reverse engineering a bit harder. But it's not really that harder because the Packer are really simple and efficient. They don't want to have problems with it. They just want to change what the executable will look like from from static analysis. And this is probably why I'm here today presenting, because the Packers are not too hard to go past them, and you can basically fairly easily understand them. So the Packers are a protection mechanism for the executables. They don't want you to look inside. So they have implemented a couple of different tricks in there to evade antivirus detection. As you should know, antivirus engines don't only apply static strings to match on a file. They are now using emulators, where they have a small module that will load an executable in memory and let it run for a while and let it unpack, so that they then can have a look at the executable file in clear form, or in its original form. So the answer by Storm was to implement some anti-emulation tricks. The first problem with emulators is that they don't implement every functionality that can be found in Windows. And this makes total sense, because you don't want your antivirus to come with a separate Windows distribution. So the Packer will make calls to exotic functions. For example, in this screenshot, it's a drag accept files. So there is no reason why an emulator would need to implement such a function. But they make a call to it and check if the result is normal. And you can see, or maybe you can't, on the left side, it checks the result. And if it's not what they want it to be, they just exit process. So that's the really small line on the left. And on the right side, they continue execution. Now, this is not necessarily obvious to the untrained eye, but I just found it by single stepping through the code. And when you see a call like this inside a Packer, there is no reason for it to be there except to trick antivirus. Or if I'm mistaken, please send me an email after the presentation, and I want to learn from you guys. The next trick, or the next step they took, because maybe this thing was a bit too easy to spot, is that they used the result from the drag query file system call, and they used it in the decryption of some pointers in memory. So if you don't return the good value from this system call, then you end up decrypting something in the wrong position, and you will execute junk code. So this is the assembly you can see on the left. Another trick I've seen about 1 month ago was to load complete executables inside the malware memory. So the emulator is not going to go around with a copy of Notepad and calc.exe. It makes no sense. But every Windows computer will have calc and Notepad. So this is wise of them. So what they did is they make the system call load library for Notepad and calc. And then they check if the handles that were returned are the same. If they're the same, then this is an emulator trying to fool around with the malware. And otherwise, then you're on a real system and you should continue executing. There has also been some obfuscation that I could see. Okay. There's also been some obfuscation. This is a small trick that I didn't spot on the first try, but once again, by single stepping through it and by reading it maybe 20 times, I could finally understand. I'm a slow person. Instead of moving bytes in memory, they will change the value of the stack pointer and then push data to a fake stack, which is actually the destination buffer. And then they will restore the stack pointer. So this is for instruction replacing a move in assembly. There has been a bunch of other tricks that could be seen inside in Storm. For example, breakpoint detection, where they will allocate a little loop on the heap, execute it, that will parse the code, and if they find a breakpoint, a software breakpoint, then they will stop execution. And also, they would redirect the execution to a new memory location, making it harder to dump memory because you're not executing the executable in its original position. They allocate memory somewhere else, and then they execute the code from there. And now, let's move forward to the rootkit and system drivers. So as you see in this outline, it's really nice to have time to analyze Storm because there's a lot of stuff you can learn from. And when I was analyzing Storm, to be very honest, I was reading the rootkit book at the same time. And one morning I was reading, the afternoon I was analyzing the code, and it's the exact same thing. So they clearly read the book before me and implemented it inside their code. So it's great. They implemented the rootkit only in some variants. I think it is because it introduced a bit too much complexity into their code, but they used it to hide the configuration file and their main executable. And the trick I found to bypass it was to grab the original executable and make a breakpoint on a system call that is create file. So whenever they create the file, you just single step a bit, and then they will write to it, close it, and afterward they will activate the rootkit. So for a moment, you have access to all the files before they start hiding. So that's an easy trick. And don't forget to rename the files afterward, because when the rootkit gets activated, it will intercept calls to the drivers that will make the file invisible. So make sure to rename the file, and then you can go on and analyze it. There has been some other functionalities as well implemented inside system drivers. So to me, that was an introduction to ring 0 debugging. In some variants, this is really small, so you don't have to. I'll just explain it quickly, and if you want to take the slides offline afterward. In some scenarios, you would get a first stage dropper in an executable that would simply write a kernel driver to disk and then start it as a service. So then you have a system driver that is running. This system driver will unpack an executable, a P executable, and inject it into service.exe. My first mistake here was to try to debug service.exe. Not good. It just froze my complete system. And afterward, I was able to find out that this executable that was injected into service.exe was responsible for all the functionalities of Storm. So for example, they were the one establishing the peer-to-peer communication and all the other functionalities. So this is interesting, but the way I found them is even more interesting. By simply reading the code inside the very good IDA, you can see that the P image is not really encrypted. It's only encoded with an XOR key. And this key is 1 byte long. So the decryption loop is really small. And by reading it, you can understand how it's working. So my first approach to find the injected code, because this is where all the functionalities are, so this is what I wanted to dump to disk and then analyze statically, was, so I decided to try the Sizer debugger. I think this is a Chinese project. It's a ring 0 debugger. It has a nice GUI and everything, so you should give it a try if you haven't done that yet. And I put a breakpoint on allocate memory. So when they're ready to allocate memory inside the service.exe process, then you know that they're up to no good and they're going to inject the code, and that what you want to have a look at has already been decoded. But this is a bit hard, and playing inside ring 0 is not really my kind of stuff. So an easier way was to implement a small script inside IDA-Python that would just make the same decryption loop on the code I had, and then dump it to disk to a separate file. These small bits of codes are probably not going to be extremely useful, but I'm going to release them, so if you guys want to have a copy, I'll be happy to share them with you. I have also included a link to IDA-Python, which is a great tool. And also, Danny Quist from Offensive Computing has made a similar analysis from this system driver, but on his side, they decided to emulate the decryption loop with x86 EMU. So that's another approach that could have been taken to decode the injected code. So that's it for the system drivers. During some of the propagation campaigns from Storm, they tried using some browser exploits. So a typical scenario would be that web links would be sent through email, and inside this email, if you click on the link, then you are redirected to a proxy, which would then send your request to a mothership that would serve malicious JavaScript. The first thing you realize when you open up this JavaScript is that it is obfuscated. But the obfuscation is not really hard to understand, because once again, it's an XOR operation. But they tell you, because the variable is called XORed string, and the plain string is called plain string. So, I mean, it's obfuscated, but it's pretty easy to understand. And they're also trying to have some nice messages. I don't know if you guys can read this. But yeah, they're playing around with AV companies. So they have two functions that do absolutely nothing except insult some other companies. And I didn't make it up. I'm not kidding. You can go and have a look. They're really doing this. So that was a good opportunity for me to learn about decoding JavaScript. The first thing I found was to replace the eval call that is always used to evaluate some JavaScript after it's been deobfuscated. And I would replace this call to eval by a call to alert, which would basically just bring a message box to your browser. But the output was way too long, and it would make a really big window, and I couldn't copy and paste from it or edit it. So since this is a very easy thing to understand that it was an XOR operation, I did a quick Python script to XOR every byte that was there in the string. But this is not a really generic approach. So after looking a bit and finding on this Sans diary, so the URL is there, I replaced the eval function with this show me function that would simply make a text area at the bottom of the page. Instead of executing the obfuscated JavaScript, it will display it in a nice text area where you can copy and paste from and then run all your analysis. Is that for me? So by analyzing the malicious JavaScript, I found out that these were the JavaScript was trying to exploit the following security flaws inside web browsers to basically download and install a copy of Storm. And whenever I would see such a list, I would just wonder, how do these guys find the list of exploits that are being used? So the lazy way is to check out Honeywalk from Jose Nazario and to grep through the file called activex.py, because the script will basically call ActiveX component with a CLS ID. And then you can just grep the activex.py for this CLS ID, and it will give you a nice reference to either the name of the vulnerability or a CVE number, a common vulnerability enumeration. And if you don't find what you're looking for with this lazy method, you can also just have a look at the code and see calls to weird functions. because the exploit code is usually very straightforward. They make 1 or 2 calls and then launch the exploit. So if you Google for these calls to ActiveX methods, you usually find either the exploit code or a description of the vulnerability. And to show you how nice and clean the code is, here is a part of the decoded JavaScript. First of all, you notice that it's all indented properly. Once again, you have all the variable names that are extremely readable. So for example, the first variable is called URL real.exe. So that's our original executable file. And then you have a call to XML HTTP download with the real executable. Afterward, they create a file name on C://sys plus get ran string. I mean, this is really easy to understand once you've been able to decode the JavaScript. So there's no black magic in there. You can simply either decode the JavaScript by yourself or use the text area trick to find out what it's all about. Now, the reason why Storm got so much attention in the beginning was because it's using a peer-to-peer network as a command and control mechanism. And I'm going to give you a bit more details on how this peer-to-peer network works. There is no time here to explain everything in details, but there has been other publications, including the one by Thorsten Ols that I referred to earlier, that can definitely give you more details. But the Storm peer-to-peer network is based on Kademlia, which is also known or used with Overnet or eDonkey. In this network, each peer is identified by a 16-byte hash, and also each information you might search for is identified by a 16-byte hash. These networks were really made to share files. So, for example, if you search for a Britney Spears video clip, they will make an MD4 of your keywords you're searching for, and then they're going to search for it. All the communications are done over the UDP protocol, and they are not using any predefined ports. So it's a bit of a challenge to be able to connect to the peer-to-peer network. So in order to connect to the peer-to-peer network, a new peer needs a list of peers to contact. So then, when you contact one of the peer that is in this list, this peer will send you a new list of other peers you can get into contact to. So you will repeat this process recursively until you get connected with thousands of other machines. Here's a really cool animation. I spent a night on this. So if you have a malware, so that's the skull, and then it comes with a list. It gives you the coordinates, so that means their IP, their hash, and the port you should communicate with. Then you enter in communication with these peers, and each one of these peers will give you the coordinates of new computers you should contact, because they are also participating into the network. And as you see as well, you will get connected with thousands of computers, but you will not be connected to the complete network. You only get into contact into enough computers to be able to communicate properly. So this is how the initial peer list looks like for Storm. It's stored on disk and usually has the same name as the executable. You see that the first field is the ID of the infected system. Second field is the UDP port it's going to bind to. And afterward, you have the list of the peers. Each line is the description of the peer. So the first part before the equal is the ID of the peer. So this is your 16-byte hash. Then the 8 following bytes are the IP address in hexadecimal form. And then the port you should communicate on over UDP. So in this case, the IP address is 66.169.14.51. By looking at the format of this peer list, and by searching on the internet, I ultimately came across the KADC peer-to-peer library. which is a C library designed for academia networks. And by looking at the structure of their configuration file and the structure of their code, it's the exact same thing that has been implemented inside Storm. So I don't think that this has been made publicly before, but Storm is definitely using KDC. So if you find something or a bug inside KDC, then you have a big botnet. Now that you're connected to the peer-to-peer network, the reason why you want to connect to this network is that you want to search for information. When you're searching for information on the overnet or Storm peer-to-peer network, you first ask your neighbors about a hash. Do you know this information, or do you have this information? If the neighbor doesn't know, then they ask to their neighbors, etc., etc. The way Storm has implemented its command and control mechanism is that every infected computer will search for a specific hash every day. So every day, all the infected computers are going to search for the same hash. And the result from these search will be encrypted, and it will be the comment to the botnet. This is usually encrypted with RSA, and it contains an update location. So every day, the Storm botnet will download a new executable and execute it. And this is very powerful because you can do anything you want with the botnet. When it fetches an executable file, let's say they want to send spam the next day, then all the information that is necessary is going to be in this new executable file. So they didn't have to implement a whole language of communication that say, oh, if I send you flood this IP, etc. No, they just send an update location, everybody downloads it and executes it. Now that you understand a bit better how the whole communication is working, I wanted to connect to the Storm's botnet and see what I could find out. But to do so, I needed to find a bit more information from the binaries. So first of all, I did a quick script to translate the peers from their, well, not obfuscated, but compact format to something that could be fed into KDC. So once again, this is a small piece of code I can release. And after that, I came across a bit more of a complex problem, which is the hash generation routine. As I told you, Storm is going to generate a hash every day, and it's going to search for it to find this hash before they would, or at the same time, and then search for this information as well. The problem with the hash generation routine is that it would slightly change between variants of Storm. And I'm still learning reverse engineering, so it's a bit of a long process to every day reverse engineer this hash generation routine, re-implement it into another language, and use it. So what I decided to do is to use Storm's code to generate the hashes. What is needed to do that is to first of all unpack the binary in memory so that I could find the hash generation routine. Once I find this routine, I use PyDBG and PyMay. I think Pedram is over there, so if you have questions on this project, he's the one to refer to. And then you make a call to this hash generation routine. So that means that you don't have to understand the complete process of hash generation. You just have to find this function in memory and call it. And there's a slight it's a bit more complex because they don't generate only one hash. In reality, they generate 32 of them because there is one byte that is random inside the hash generation. So instead of calling it once, you call it 32 times, and you're going to get all the hashes you are looking for. So I'm going to show you quickly how I did that. So let's start with this video. I've started using Immunity Debugger. It's pretty nice. If you haven't played with it yet, I strongly recommend it. The executable I have used for this demonstration is like a month old, so the code might have changed a bit. The first thing I do is I scroll down and read the code. You see it's relatively understandable. You can have a look later on. But it's not doing like funky function calls and everything. It's plain assembly, straight assembly, decoding. And so what I did is put a breakpoint at the end of this decoding code and let the program execute until we reach this point, and then step into. Then we hit a portion of code that has not been analyzed before, meaning that it has been decoded. So what I do is I hit the analyze button, then we see that we have more code with calls to load library and get proc address. So this is the process where the import table is being rebuilt. Once again, I simply put a breakpoint at the end of this portion of code with call EBX and let the program execute it. So of course, this is something that is going very quickly for you. But by simply stepping through this code slowly and trying to understand what it was trying to do, after a couple of hours, you can understand that it's relatively simple and only decoding some assembly inside memory. And now that we've reached the end of the import table reconstruction, we once again step into and we reach the original entry point. Now that we reached the original entry point, I'm very lazy, so to find the hash generation routine, I simply search for the first 10 bytes of this routine. And I haven't had any problems with that yet. It's not really nice. I mean, I could have had a much more elegant solution, but it has worked so far. So now I have all the information I need. I used the script that is present in PyMay that is called remote debuggy call, I think. And I've slightly modified it to execute a variant of Storm, put a breakpoint everywhere I needed to in order to reach the original entry point. Once I have reached this original entry point, I use it to call the hash generation routine. So this code is also going to be available if you're interested. And once we've found this information, we can simply launch the script and give it as an argument the executable that we are analyzing. So basically, why is this useful? It's because you can fetch a binary that you've never seen before, and the only thing you have to do is to unpack it. And then you can use it to find the hashes that are going to be used by Storm every day. So when you're ready, you hit G, and then it's going to list all the hashes. So we have all the 32 hashes we were looking for. And that's it. So of course, there are lots of things that could be improved with this demo. I should change the binary match to something a bit more elegant. Also have more interesting unpacking techniques, and save the results to something else than printing them to the screen. Earlier this winter, the guys behind Storm made a significant change. Well, it's not really significant, but a change that threw away lots of researchers when they started to encode their communication. Because before that, you could simply parse the traffic with Wireshark and decode it as eDonkey traffic, and you would understand everything. You see the search request, search result, and everything. And they probably realized that there were too many researchers paying attention to what they were doing. So they tried to obfuscate their communications. And what they did is, once again, they used the XOR operator to encode all their traffic. But the messages have the same length, and the constant values are the same. So I didn't find this, Joe Stewart did, but we had access to earlier messages. So message from yesterday were not encoded, they looked like this, and then a new message today is encoded. But they had the same length and everything. So you could just XOR the two of them and find the key that was used. After that, I was able to search a bit inside the code. And when you look for calls to send to and receive from, then you see that just before them there is a call to the encoding routine, and just after them there's also a call. So this is what the encoding routine looks like. And the key is only 40 bytes long. So what I did is, because you have to remember that my objective here is only to connect to the Storm botnet and understand what's going on. So what I did is I grabbed a copy of KDC, grabbed a copy of the peers. I patched the communication routine to have the XOR before sending data and after receiving data. And now that I have all the hashes that I want to look for, well, I just put them inside the small program and it's going to work. So that's it. This is how I learned reverse engineering with Storm. My conclusions are, first of all, that Storm's authors are reading a lot more books than I do. And I thank them for teaching me that much on malware this year. But it's very hard to describe exactly what they've been doing and where they are going because they are in constant evolution. And the reason why this threat is really interesting is not only from the technical level but also for the coordination of all their operation. For example, they will always make big operations around dates where no IT professional is going to be working, Christmas Eve, New Year's Eve, or when there's a big storm hitting or everything. So they have a very interesting operation, and I think this concludes my presentation. A big thank you to these guys that have helped me a lot inside and outside ESET. And if you have any questions or comments, I will be glad to address them. Comment. Yes. Yes, there has been. The question is if I've considered poisoning the network. Personally, I haven't, but I know that other researchers, for example, Thorsten Olds, he did it, he tried, and he also measured the efficiency of his poisoning. And yes, if you know what the hashes are going to be searched for tomorrow, then you can try to poison it. But you probably need a lot of bandwidth. And what they did is that they made a custom client that will try to establish connection with every node on the botnet, meaning that if any of them is asking for a certain information, they're going to be the first one answering this. So this was a good way to poison the botnet. They did it for like a week, and then they stopped because it was only for research purpose. And I don't think that anybody really has the legal power to do that on the long term. But yeah, that could be a solution.
You mentioned that they are selecting just subsets of the botnets for particular operations. How do they do that? Because all the machines are going to be searching for the same keys. Is it at the executable level, or?
The reason is, I'm not sure. I think that they can redirect some of the, because every time you make a request to update your executable, then they know where you're coming from or what you're doing. So when you're asking for an update, then they can probably redirect to one file or the other to make sure that you do what they want. For the what, sorry?
The very valuable service that you did in explaining some of the ignorance.
Oh.
I'd like to ask you, if you had to rank order in terms of complexity and especially the analysis time, the 5 or 6 defense measures that they built in so that you wouldn't figure out what happened, what was the hardest enough to crack a priori, and what is the hardest enough to crack once you know your process goes?
I think well, this is for myself, right? Probably not, it would be completely different for other researchers. But for myself, it was the ring 0 code, because I'm not really used to playing inside the system drivers and such.
Let me ask a follow-up question. They didn't write books. They were very gifted, but they were not professional scientists. They used them for hashes, they used XOR ciphers. All this can be made much better and much more opaque. Once real professionals do this with these techniques, it will become virtually impossible to do what you're doing right now for much longer. So what would you recommend?
I completely understand what you're saying, and this is a very good fact that lots of people are saying that it could be worse. It can always be worse. But what they have to take into account is that they want to maintain the complexity of their creation as low as possible and as maintainable as possible. And simply applying an XOR key to their network traffic was enough to throw researchers away for like 3 weeks. Well, maybe less for gifted ones, but yes, but I totally understand. They don't necessarily have enough incentive to make big steps in making it harder to reverse engineer because they're already winning. Antivirus products can detect this threat, but the authorities are not spending money to really hit this botnet or anything. So, yes. Do we have time for this? Is this okay? Yeah. Yes, and this is probably why I'm presenting here today. But yes, this is right. Probably anyone that has really paid attention to reverse engineering has also paid attention to software piracy protection and things like that. Is your question toward, are they going to move to a more legit business or? Yes. It's a good point. They have definitely a lot of experience inside in reverse engineering, and they were able to probably reverse engineer antivirus products to find flaws inside their emulators. So they definitely know about software reverse engineering. But I think that at the moment they're doing a lot more money than they would ever do inside the legitimate business. So they're just going to continue inside this. So if you have any more questions, you can take them offline or send me an email. I will be more than happy to answer them.